Good morning, everyone. I hope you are doing well. Can you all hear me okay? Okay, cool. Let's get it started with announcements as usual. So, I was looking at the views for the video solving ODEs with Laplace, and then I was checking out the online homework assignment. And it looks like there weren't any problems that I saw as far as solving a full differential equation with Laplace for yesterday's online homework assignment, but there are some today for sure. So I wanted to point you to that video in case you haven't watched it yet. That will be something that's a big part of this 2 weeks that we're looking at solving with Laplace transforms. There was the video Laplace and inverse Laplace, and that seemed like everyone saw it or most people saw it. But there was also a video solving ODEs with Laplace that you'll want to watch because that'll have a really important concept that will be prevalent throughout this 2 weeks. All right, yeah. So I just wanted to direct your attention to that yesterday there were two videos, which maybe wasn't clear in the topic outlines, but that's certainly a video you'll want to watch if you haven't seen it, the solving ODEs with Laplace. With that, why don't we go ahead and jump into any questions that you have that you'd like to go over? So, questions you've got. First question I see, can we review the fraction splitting? Yeah, sure. So that is called partial fraction decomposition in general. We can certainly go over that. It's a thing that pops up quite a bit. All right, so how does partial fraction decomposition work? You essentially have something of the form, how do I want to say it in general? Well, as a specific example, you might have 1 over, let's say, s cubed plus 4s squared. And if you have something like this, or it could even be something else up top, like let's say s plus 5. If you have a rational expression here where it's a ratio of two polynomials, then as soon as you have the numerator being of less degree than the denominator, you can use partial fraction decomposition. I'll just set up this particular case to get into it, and then we'll look at more generally how it works real quick. But what you can do is you can say this is going to be equal to s plus 5, factor the denominator, we would get s squared, and then s plus 4. And it's that factoring that really sets up the whole decomposition. So when you factor, and if more generally I say this, that we have some, let's say, capital F of s over lowercase g of s, the goal is to factor the denominator completely. And I should say that the degree of capital F is strictly less than the degree of g. If it's not, you want to divide until this is the case. But you factor this g of s over the real numbers, and you're going to get a few possibilities for what your factors could be. Jumping back to this specific case, if I were to write this out, it happens to be that we follow this formula and get the following, like this. Now, knowing how to set that up depends on knowing what you should do for each of these factors. So if we are factoring, let's say this g of s, you could get a variety of things. You could get repeated, how do I want to say it? I guess repeated linear terms or repeated linear factors. That's one possibility. So that would be something like s, maybe s minus a, I'll say. And then that's raised to some power n. And then you can get repeated irreducible quadratic factors, which would look like something to the effect of s squared plus bs plus c to some power, maybe m. And depending on which factors you get, there are certain ways to set up what the sum will ultimately be. I'm going to remove this just for the moment, or actually move this to the other page. so that we can see more generally what's going on. So here's our setup. We have a rational expression. The degree of f is less than g. And I'm saying that they're in terms of s because the place we're likely going to be using this right now is when we're in the S space. We're going to be doing algebraic manipulation. So that's why I'm setting up as polynomials in S. Now I mentioned you can get one of two things, and it's true. You can get repeated linear factors or you can get repeated irreducible. Any polynomial with real coefficients can be factored down into only repeated linear factors and repeated irreducible quadratic. You could get quadratic, but then reduce it. But some of them won't be reducible or factorable anymore over the real numbers. So when I say irreducible, what I mean there is over the real numbers, i.e., they have complex roots, but not real roots. Now, if you have repeated linear factors, what you're going to do is you're going to have, let's say, some a sub 1 over s minus a plus a sub 2 over s minus a squared. And you're just going to keep scaling it up until you get to a sub n s minus a to the n. Notice that the coefficient is just a constant in each case in the numerator. And then you have a number of terms equal to n, where each term differs by the fact that you're scaling up the denominator by one more degree each time. With irreducible quadratic factors, it's very similar, where you start with s squared plus bs plus c. And then the next one is like above, s squared plus bs plus c squared, and so on, till you get to the, kind of running out of room there, until you get to s squared plus bs plus c to the m, because that's m here. But what's going to go on top is a first degree polynomial. You think of a constant as a 0 degree polynomial. Since here we have an irreducible quadratic or second degree, up top we'll have a first degree. So that might look like a1s plus b1, a2s plus b2, just generic first degree polynomials. And then that's it. Once you've determined what you should write out, then there's a bit of an algebra. And it's a little bit hard to do in general. So maybe I'll finish with that specific example. So if we had, I think it was s plus 5 over s cubed plus 4s squared, we could factor that as s plus 5, s squared, s plus 4. And now I claimed that you could write this as a over s plus b over s squared. Actually, maybe I'll keep consistent with before. A1 over s plus a2 over s squared plus, let's say, b1 over s plus 4. After that, now you're going to do really just some basic algebra where we're going to take the denominator, multiply that on both sides. So if this is the denominator, I'll color this cyan here. We multiply both sides of this equation by that denominator. And the result on the left-hand side will, of course, be s plus 5. And then on the right side, we distribute. So distribute each of these terms like so. And then we get ultimately a1 s plus 4 plus a2 s plus 4 plus, let's see, b1 times s squared. And now you'd like to know what a1, a2, b1 are. So now we'll do some substitution. That is, we'll choose s to be particular things to end up with some equations and try to solve for a1, a2, and b1. So let's, now that we have this thing, let's let S be equal to, let's see, how about -4? I chose -4 so that these two will disappear. So we have -4 plus 5 is equal to A1 -4 times 0 plus A2 times 0 plus B1. And I guess that's going to be 16. And then now we get 1 is equal to B1 times 16, or that 1/16 is equal to B1. And you can do the same thing where you, let's say, let S be 0 and then pick S to be 1, or you can do a variety of things. You may not immediately end up with, when you substitute A1 is equal to whatever, but you'll have, let's say, 2A1 plus 4A2, and then you can get another equation that's like 3A1 minus 2A2 or something like this. And then you can do the usual substitution or elimination from there. But that's the outline. So setting it up as a sum like this, knowing which terms you're supposed to have, and then doing the algebra so that you can solve for this A1, A2, B1. So hopefully that is a good review there, or kind of gives you an idea what's going on. I'm going to move to the next question. So I'm going to ask, what's the benefit of using Laplace instead of the characteristic polynomial? Let's see. Sometimes it's a good question. What is the benefit? Oh, I know. Because if you have a homogeneous differential equation, it's probably easier to use a homogeneous linear constant coefficient differential equation, probably easier to use the characteristic polynomial. But in the case where it's non-homogeneous, it would probably be easier. So if you had, let's say, 3x double prime plus 2x prime plus, actually, or if it's higher than second degree, let's even say we had something like this: 3x the fourth order plus 2x to the third order plus x double prime minus 8x prime plus 5x is equal to cosine of 2t. And in order to use the Laplace transform, what you need is some information, initial value information. So if you had an initial value problem like this, you could certainly find the characteristic polynomial, since it's constant coefficient homogeneous, or constant coefficient linear. You could find the characteristic polynomial, find the roots of that, and then that would give you the complementary solution. Then you would want to find a particular candidate and then feed it through here. And all that could be quite involved, because you'd have to first find the roots of a fourth degree polynomial, which, depending on the polynomial, could be quite cumbersome. Then you'd have to set up your particular solution, which would have a cosine and sine term. You would then feed them through this differential equation. And even if there wasn't a t in your particular solution, if it wasn't like t times cosine, even still, it's going to be quite a lot. So the process, I think, would be kind of long here. With a Laplace transform, especially if you have something like these are zeros, or a few of them are 0, I think it would go much faster to use that on this. So for higher degree polynomials, it's a little more efficient. And even for lower degree polynomials or lower order differential equations like this, it lets you find the full solution right away without having to find the complementary, then find the particular, then do the substitution of all these. The Laplace transform essentially does everything all at once. So when you go through the process, you just get the solution completely with all the parameters solved for the particular solution, complementary solution all together. It sort of does it all at once, which is nice. So to review the characteristic, like what are all the steps you'd have to go through? Polynomial method. You'd have to find polynomial. That's not hard. But then you'd have to find the roots. you'd have to set up x of c. You'd have to guess a x of p. You'd have to feed x of p through diffie q. Then you're not done. Then you would construct x, which is equal to xc plus xp. And then you'd have to solve for parameters. And that could be quite an involved process. Laplace transform, on the other hand, you simply apply Laplace, you algebraically manipulate, probably a partial fraction decomposition. And then you take inverse Laplace. And then the end. Maybe you have to do a little bit more manipulation after that, but that's essentially it. Okay, so that's a good question. Next question. Could we go over question 1, part A on homework 5? Yeah, let's maybe check that out. Homework 5. I'm assuming that's written homework 5. Consider the following example of predator-prey. Okay, so 5.1, part A. What do we have? We've got dx over dt. So the change in one population depends on the populations of itself and the other one. And then the change in the other population also depends on the two respective populations. And this says do the following. Use the fact that dy dx is can be written as dy dt over dx dt. Just thinking of that in an algebraic way, it's like you have dy over dt times dt over dx. So in some sense, there's like a cancellation effect here. And the reason you would want to see it this way is, well, we know individually what dx dt and dy dt are. So you would just write now dy dt is exactly this, which I'll put in one color. And then dx dt is this. And that gives you xy minus 3y divided by 4x minus 2xy. And now you've got a first order differential equation. And it's just in terms of x and y. I'm trying to see. Rewritten. So let's see, how can we rewrite this? We can rewrite this as y, x minus 3, and then divide it by, factor out an x times 4 minus y. And now I think you have a separable differential equation. So we have dy dx is equal to, and just to be clear, here's everything in terms of y. And then here's everything in terms of x. And if we just do a little bit of a rearrangement, we can see that it's separable. Where we have x minus 3 divided by x. And then we have times y divided by 4 minus y. Now you have a separable diffie-q, so you can multiply, divide appropriately, integrate, and then so on. And the problem states that you might have something kind of like this, where it's, I'm not claiming this is it, but just to give you the idea of what implicit is. So you might have something like so, and this is certainly not it. This is just an example, but you might have something where you can't really separate the two, the x and y. So if you end up with that, it's saying that's okay. Okay. With that, why don't we get into the rest of it just for the sake of time? So let's get into convolution. Let us start with what linearity is and is not. So what does it mean to be linear? So we talked about this as a little bit of review to start with. So to be linear means that, let's say if we just look at the Laplace transform up here, what we have is taking the Laplace transform of this linear combination where it's f plus g, but it's a scalar multiple of f, namely alpha, plus a scalar multiple of g, namely beta times g. And what you can do is you can, one, separate across addition, and then two, you can factor out or pull out these constants. It's the same thing with the inverse Laplace transform. Now I've written functions of s instead of functions of t, but it works out exactly the same. And I also want to back up and say, if I didn't get to your question, it's just I saw the other questions earlier, and just for the sake of time, we'll go forward. But I think your questions might be answered. Well, at least one of them. You'll see an example of it, I think, as we go through this. And if not, you can stick around and ask me afterwards if you have time. So to be linear means we can take Laplace of this linear combination and rewrite it like this. And inverse Laplace transform is also linear, so we can take this linear combination and rewrite it like so. Now, as I've highlighted here, this is a property of addition and scalar multiplication. So we don't see regular multiplication of functions in this. We're multiplying scalars times functions, but we're not multiplying two functions together in any of these expressions here. So we can't just say Laplace transform of, let's say, one function times another, f times g. We cannot say that it is equal to the Laplace of one times the Laplace of other. That is not true. It may be true in some rare case, but in general, it is 100% not true. So we don't have that. But there's something else that we have. If we do end up with the Laplace transform of one thing times the Laplace transform of another thing, there is some other thing we can write that's kind of similar, but not exactly this. And that's where convolution comes into play. Now, someone already asked this, and it was, I think, a good question to open with. They said, what's going on with this partial fraction decomposition? What are you doing there? Well, as I kind of mentioned, and here's another specific example. What you're doing is you're taking something like this, 1 over s squared minus 4s. You can write that as a product. If you factor out the s here, you have 1 over s times 1 over s minus 4. And what you're doing with partial fraction decomposition is that you're taking a product and you're rewriting it as a sum. So that's an important thing to be able to do, to go from a product to now a sum. Okay, well, at first glance, you may think, well, who cares? You're just rewriting it. Well, why that matters and is useful is because, I'll jump back to the previous page. It's because the Laplace transform can be factored over a sum, or can be distributed over a sum, or however you want to say it. We can take a sum and then we can rewrite it, where we're essentially taking the Laplace transform of smaller or simpler parts. So if you start with the Laplace transform of a product, let's say you have something like this, or let's say you want to find the inverse Laplace transform anyway, of a f of s times g of s. We said it's not the inverse Laplace of capital F of s times the inverse Laplace of capital G of s. But with the partial fraction decomposition, what you might say is that you can rewrite this product as a sum, and maybe that sum looks like, maybe I'll do h of s plus k of s, where you've changed from product to sum. And once you have a sum, since Laplace and inverse Laplace are linear, you're able to break it down into smaller pieces, as it were. So we started with, let's say, inverse Laplace transform of a product, and now we have a sum of two inverse Laplace transforms, where presumably these we know how to find the inverse Laplace transform of. So converting from product to sum is what partial fraction decomposition allows us to do. But you can also recognize a product in the S space of F and G, let's say, and then use this thing we're going to look at, which is called convolution. This is an alternative way to go through this process. Sometimes it will let you, trying to think if you can always use partial fraction decomposition. In most of the cases we'll look at, you can, but some you cannot, or it will be very difficult, and it would be faster to use this convolution. So it lets you get around some cases that might be either impossible or hard with partial fraction decomposition. And well, yeah, that's essentially it. So let's see what's going on with it. So here's what convolution is formally. If you have a function, let's say f, and a function g, and they both go from the non-negative real numbers to the real numbers, they could be defined on a larger domain, but we'll say at least they're on the non-negative real numbers. We say the convolution of these two is as follows. The convolution of f and g, which is f star g, of t is equal to this here. Now I should also highlight perhaps t, because t plays the role of being both a variable and a constant. When we're trying to find the convolution of f and g, or f with g, of, let's say, a certain value t, you can consider that thing fixed here, t to be fixed like that, and then it fixed there. What you're integrating with respect to is this a. In the Lebel book, I think it calls it tau. You may see it as other variables. It doesn't matter so long as it's not t. This has to be distinct from that. I'm using a just because it looks much different than t, to really highlight the fact that you have a different variable you're integrating with respect to. But notice, while you're doing the integration, t acts as a constant. And that's because you're not integrating with respect to t, you're integrating with respect to a. And yeah, just to highlight from the previous slide, it is not true, 100% not true, that the Laplace transform of f of s times g of s is equal to the Laplace transform of f of s times the, I should say, the inverse Laplace transform of g of s. This is decidedly not true. Yeah, and that's why we use partial fraction decomposition to switch to a sum. But you can actually still work with this where you have a product, but instead of converting via partial fraction decomposition, what you can do instead is use this convolution that we're setting up here. So you have, and I'm going to flip back, you have essentially two ways to go about it. Partial fraction decomposition, which sometimes may be too difficult, or not necessarily too difficult, but it may be much harder than just using this convolution here. Sometimes convolution is just much cleaner and faster. All right, so we're looking at what is convolution, and I've given this formal definition. And now let's see how this actually works in practice here. Let's jump to, actually, before we jump to another computation, I want to give another example just to really highlight. If you had, let's say, f convolved with g of, let's say, 2, what this would mean is you're computing the integral to be 0 up to 2 of f of a, g of 2 minus a, and then dA, where again, the a is the variable that you're integrating with respect to. So I really want to highlight the fact that whether it's t here or whether it's some given number, you're going to take that and treat it as a constant when you do the integration. All right, now let's do actually a computation here. So convolution. We have f of t is cosine of 4t. We've got g of t is sine of 4t. And they're certainly defined for t greater than or equal to 0. They're defined more than that, but we'll say at least for t greater than or equal to 0. And let's say we want to compute f compose or f convolved with g of t. Now we could do it individually for a given t value, like let's say let t be 3 or whatever, but we can also try to do it in the general case where we just think of t as fixed for the moment, like it's a set thing, act as if it's a constant, but we let it be general so that we can later substitute in. So we kind of do more work at once. And in this particular case, we're going to use this identity. So I've written this up here. And someone asked a question. I'm going to flip back. What if you had the other way? What if you had g convolved with f of t? So the first thing that you have on the left, that's going to be, actually, let me write this a little nicer. If you have g convolved f of t, the thing that's on the left, in this case, the g, that's going to be the first thing you write. So you'd have g of a. And then from there, you'd have f of t minus a. So notice that we switched these two. F went first, or f went first in the first case. So we put f here. G went first in the second case, so we put g here. And this thing, I think most commonly it looks like the asterisk. So someone asked, what symbol is this? If I sort of blow it up, I think looks like this. Just checking really quick. Yeah. So it's an asterisk, or I think you may sometimes see it as a star, like this. One of these two. Okay. So flipping back here, we're going to use this identity. Let's set up the convolution. And just to be clear, here's G, here's F. Actually, just let me color them like so. So we've got G, we've got F. To make it clear what we're doing here. So if we take F, compose G of T, by definition, That's going to be the integral from 0 to t of f, which is cosine of 4, but now not t, but a, times g, which is sine of 4, but now instead of t, what we have is t minus a dA. Now I'm going to do some coloring here to help us follow what's going on. So we've got this. T we can consider to be fixed. Excuse me. Then we're going to have A, which is what we integrate with respect to. All right. A lot of colors going on, but for starters, at least, we just want to see what goes where. We started with f on the left. That's the first function we put here. Where notice all we've done is we've replaced t with a. Then g goes second. So that will be the second factor here, where we have sine of 4t. But instead of saying 4t, we say 4 times t minus a. So in one case, we substitute a, the other case, we substitute t minus a. Now I'm going to take this and put it onto the next page just for the sake of having some room. And then now that we've seen how this is constructed, I will maybe actually take the color away to be a little less distracting as we work through this. So we'll turn this to here. All right, now if we look and we see this cosine of theta, sine of psi, there's a trig identity, which allows us to rewrite it like this. In this particular case, this is going to be our theta, this 4a, and then sine is going to be, or the psi rather, is going to be this here. So if we rewrite this using the identity, what we get is 1/2 sine theta is 4a. That's here. So we have 4a. Then we have plus psi. So we say plus 4t minus 4a, because psi is 4t minus 4a. Then, continuing the identity, we have minus sine theta, again, is 4a. And then we have minus 4t plus 4a. Now, here again, what we had was an instance where there was a product and we've converted it into a sum. And that's actually because integration works very similarly to the Laplace transform in that it's nice to work over sums and differences as opposed to products. If we simplify some of this, what we end up with is the integral from 0 to t. Actually, I'll factor out the 1/2 while we're at it. And we get sine of 4t minus sine of, let's see, 8a minus 4t dA. And now we can break this into two integrals. We can say 1/2 0 to t of sine 4t dA, and then minus 1/2. Now I'm going to ask you guys a question coming up here, namely, and this will kind of tell you if you're getting what's going on with all these different variables. I'm going to ask you what this first integral is. So in a second, see if you can figure out what this integral is, this first one. And then I'm going to keep writing this for now. So I'm going to ask you what that is. Let me actually move this to another page. But again, I'm going to ask you what that integral is. So this integral here, it's kind of an example integral that helps see if you're tracking what's going on with the constants. So what do you think this is here? What should I write for this first integral? You just want to put that in chat, whatever you think it is. Again, right or wrong, I'm not judging. I'm just kind of curious where you're at with this. Yep, the whole thing. What is this going to be? While you guys are, and I thank you for those who've put something in here. I'll give the rest of you a little bit more time to just take a guess. If you're not sure, you can just take a guess at it. But I'm going to, in the meantime, do this. And then I think we'll find that this is plus 2 cosine 8a minus 4t evaluated from 0 to t. Do I believe that? Minus, no, the other way, 16th. Okay. And I should say this is a is equal to t, a is equal to 0. All right. I've gotten a variety of responses here. Let's see what it is. I'm not going to call anyone out or anything. I was just kind of curious what you got. One way you can rewrite this is by pulling out the sine of 4t or factoring that out. Notice that we're integrating with respect to a. Sine 4t does not have an a in it. So as far as the integration is concerned, sine of 4t is constant. So we can factor that out, get sine of 4t divided by 2, the integral from 0 to t of just dA. Then in the next step, we get a, because the antiderivative of 1 with respect to a is just a. And then we're evaluating that from a is equal to 0, a is equal to t. At the same time, maybe what I'll do is this other integral. So we get minus 16 times, first substitute in a, we get cosine of 8t minus 4t. Then we get minus cosine of negative 4t. And we do the substitution in for the other case, we'll get sine of 4t divided by 2, t minus 0. So I'll just put t. And then we get minus 1/16 cosine of 4t minus, and I'll write cosine of 4t because cosine of negative 4t is the same as cosine of 4t. That's because cosine is a even function. Whether it's plus or minus, it's going to be the same thing. So in the end, we get, maybe I'll rewrite it, get t sine of 4t divided by 2. And the reason I asked you guys to chime in is because it can be a little tough to keep track of these variables, and why I tried to stress that the a is what you're integrating with respect to. When you have a case where you're integrating with respect to a, but you just have something with a t in it, you can factor that out, because as far as this integration is concerned, it only cares about integrating things with respect to a. Everything else is constant. So that factoring out then made, I think, this a little bit simpler. So that's how we do that one. Let's maybe look at one more for the practice. Now let's say we have f of t is e of t, g of t is just equal to t. So I'm going to ask a question. Why didn't you take the other one as a constant too? Oh, yeah, good question. So in this case, notice we have sine 4a minus 4t, or 8a minus 4t. But importantly, we have sine of something involving a. Since we're integrating with respect to a, we don't treat it as a constant. So here we have sine 4t, no a, and we're integrating with respect to a, so we can factor that out. In the second case, we have sine 8a minus 4t. We're integrating with respect to a. So there's an a here and here. All right, in this case, if we have f of t is equal to e of t, g of t is equal to t, for t greater than or equal to 0, at least. It's more than that, but we'll have that at least. Let's set up the convolution. How this looks is, again, we go the integral from 0 to t of, the first one is going to be e to the a, and then the second one will be t minus a. So here we had e to the t where t is equal to a. And then here we had, actually, let me really stress that here. This one, what we had was we had e to the t, and then we just substitute a for t. Or maybe we say t gets sent to a. In the second case, we had t, because that's g, and then we take t and we send it to t minus a. So there's two different replacements. We replace it just with a, or we replace it with t minus a. And then we're integrating this with respect to a. Now, if we distribute the e to the a, what we'll get is 0t, then t e to the a minus a e to the a dA. And I'm going to break this into two integrals. I claim one will be an easy one, and then the other one will have to do a little bit more work. One integral will be like this, and then I'm going to ask you guys which one will be the easy one. See what you say. Then we'll get this. So there's the first integral and the second integral. My question to you, and you can just say in chat, and again, right or wrong, I'm not judging, I'm just curious. Do you think the first one or the second one will need to do integration by parts on? So which one is the one that will require integration by parts? And the other one will be the easier one. So which one requires integration by parts? The first one or the second one? Okay. Yeah, good. I'm seeing a lot of responses that are pointing out that indeed the second one will require the integration by parts. The first one, like before, if I just, actually, let's put this on another page. The first one, like before, since we're integrating with respect to a, we can factor out anything not involving a. So we can factor out the t. But indeed, the second one will require an integration by parts. And maybe I'll give myself some room here. So the integration by parts of the second one says that u should be equal to a. So du is dA. dv should be equal to e to the a dA, which means v is equal to e to the a. And this will then be minus uv, which is a e to the a, minus v du, and v, so it's e to the a dA. And moreover, this should be a is equal to 0, a is equal to t. All right. And now with a little bit more work, I think we get this here. And then we get this, a is equal to 0, a is equal to t. And then finally, we get another one of these, e to the a. And if we substitute in everything, I think what we'll get is t e to the t minus 0. Then we get minus t. Nope, that's not true. We get t, well, we get t to the t, that's true. And then we substitute in 0 for a, then we get minus t e to the 0. Subtracted from that, we get, I can give myself more room here. We get t e to the t minus 0 times e to the 0. And finally, minus e to the t. And no, this was minus, so that's plus. E to the t minus e to the 0. And what we get in that case is, I think, assuming I did this right, I think I may have missed a sign somewhere. I'm not sure. But it looks like we'll get minus t plus e to the t minus 1. Actually, that looks okay. Yeah. Okay, so we went through all this, and here's what we get. That was doing the convolution. Okay, so we've seen how to do some convolutions. Now let's look at how this interacts with Laplace transform. So we've talked about the convolution, but we haven't talked about why do we care about it when we're looking at Laplace transform. All right, well, let's see. So we have the following theorem and then a corollary. And a corollary is just a result that follows very easily or quickly from a theorem. Like it's something that's kind of like, oh, by the way, also you get this. So the theorem is usually a more important or difficult thing to prove. I don't know that it's super difficult in this case, but it certainly is important. So it's worth calling a theorem. So if you have f and g and they have defined Laplace transforms, you may see it that listed as being of exponential order, but for us, that essentially just means that they've got Laplace transforms that are defined. And all the functions we'll be looking at are of exponential order. They all have defined Laplace transforms. What you can do is say, start with the convolution, take the Laplace transform of the convolution, and you get the product of Laplace transforms. So remember we said before, we didn't have the case where you could take this. So I'm gonna do this in red. This is what's not true. It's not true that f of t times g of t, when you take the Laplace transform, is equal to this. So seeing what is not true, I think, can help elucidate what is true. So notice if we just take the regular multiplication of two functions, like we do regular multiplication all the time, it's not the case that that's the product of the Laplace transforms. However, if you take the Laplace transform of the convolution, that is the product of the Laplace transforms. So this is the important result. And then it follows very naturally that if you take the inverse Laplace transform of the product of two Laplace transforms, what you get is the convolution of f and g respectively. So if you have a product in the S space, just a reminder that this product takes place in the S space, and you take the inverse Laplace transform, then that's going to be equal to the convolution. And maybe let's look at some examples. So let's actually, I'm going to make one up really quick. And this will answer, I think, maybe Marissa's question. Someone was asking about doing the inverse. I can't remember. Someone asked about doing the inverse. If you have, let's say, just simply to get ourselves kind of oriented, if you take the inverse Laplace transform of, say, 2 over s cubed, that's going to be, I claim, equal to t, let's say it's going to be t squared. Is that right? Yeah. Now, the reason it's equal to t squared is if you look in the Laplace transform table, what you have in that case is that there's t squared, or maybe t to the n specifically. That would be essentially your f of t. And then over here is your Laplace f of t, which is sometimes denoted as capital F of s. And that there is going to be n factorial over s to the n plus 1. And if we substitute 2 for n, we get 2 factorial, which is 2 times 1 is 2. And we get s to the 2 plus 1, or s to the 3. Therefore, since this is telling you the Laplace of t to the n, or let's say t squared, is equal to 1 over s cubed, if you now take the inverse Laplace transform of the Laplace transform of t squared, that's like taking the inverse Laplace transform of 1 over s cubed. So notice here we're just applying the inverse Laplace transform to both sides. And in doing so, the Laplace transforms will cancel here, leaving us with t squared is equal to the inverse Laplace transform of 1 over, 2 over s cubed. My apologies. So if the Laplace transform of t squared is 2 over s cubed, then the inverse Laplace transform of the right-hand side now becomes t squared. So notice the difference between this one and this one. And now what we're saying is if we have convolution, we're able to find an inverse Laplace transform. So let's look. Say we have the inverse Laplace transform of this here. Now, there may be something like this in the table, but I don't remember exactly, but I don't think a form like this is just listed explicitly in the table like so. You have to do a little bit of manipulation to get it to line up with a line in the Laplace table. So if you look at this, one way we can rewrite it, take s over s squared plus 4, that whole quantity squared. We can write it like this, as s over s squared plus 4 times 1 over s squared plus 4. Then we can take and write this one the same again, but take and do 1/2 times 2, which is 1, so that we get this form. Then I'm going to write it like this, 1/2 times this thing, s squared plus 4 times 2 over s squared plus 4. Now I'll write it like so. 1/2. Now, just out of curiosity, do you guys remember what is s over s squared plus 4 the Laplace transform of? So what is this one? That's my question to you, just to see if you kind of remember it or you can find it quickly in a table. Just kind of see where your Laplace skills are at. So what is this the Laplace transform of? And I'll finish writing this over here. And I'll color these just so that we see how they match up. Okay, I've saw a couple of you got it for sure. Indeed, it is cosine of 2t. Now what you have is a product. You know what the Laplace, what you're taking the Laplace transform of in each case to get this, either cosine 2t or sine 2t, like so. Now, if you apply the inverse Laplace transform way back to this thing to begin with, because that's just what's on the left-hand side, we get that is equal to s squared plus 4 quantity squared, which is equal to, I'm going to use linearity and write this as 1/2 Laplace inverse of this product. Actually, maybe I'll just copy paste. All right, now we're taking the inverse Laplace transform of a product of Laplace transforms. Based on what we just said to the theorem, which I'm going to jump back to. Here we go. So if because the Laplace transform of a convolution is equal to the product of the Laplace transforms of each part individually, going backwards, it should work out similarly. You're taking the inverse Laplace transform of a product of Laplace transforms. You should get the convolution. So again, it's easier for me at least to remember the first part and then get the second part from it, or remember the theorem and get the corollary, but whichever way it's easier for you to remember. But the Laplace of the convolution is the product of Laplaces. So taking the inverse Laplace transform of that, just applying inverse Laplace transform to both sides, you'll cancel it out on this side, leaving you with just the convolution. So if we look at this case, I'm going to erase a few of these steps and bump this up. Now the inverse Laplace transform of s over s squared plus 4, that quantity squared, is now going to be equal to, and maybe I'll even stress why we can write this. This follows from that corollary. So what we get in this case is that it's the convolution of cosine 2t convolved with sine of 2t. And then that's really it. Now notice what we could have done is we could have rewritten this using partial fraction decomposition. That would have been fine, but there would have been a little more work to do there. But it's true, we could have used partial fraction decomposition. So just a note, we could have used partial fraction decomposition. So that's a possibility, but it would have been a little bit of work, essentially because we would have rewritten it as a sum where there's like BS, just to kind of see what it looks like. Would have been, maybe I'll write it, A1S plus B1 over S squared plus 4, and then plus C1S plus D, or A2, S plus B2 over S squared plus 4 squared. So we would have had to write it like this and then solve for A1, B1, A2, B2. So there would have been 4 parameters to solve for. And then we would take the inverse Laplace transform and so on. So there would have been a lot more steps here with partial fraction decomposition. Possible, but more steps. Here, we, with not too many steps, have found that it's the convolution. Now, the convolution is an integral, so there's more computation to do there. But sometimes it's just nicer to have something right away instead of going through all these extra steps. Sometimes this can give you enough information to say whatever you want about the solution of the problem. And at this point, it's really it. Like, it's just the convolution. If you want to compute it more, we could compute it as the integral. So you could set up the integral, which just for reference would look like this: cosine 2a times sine 2t minus 2a dA. You could use a similar identity to the one we saw in the first computation we did with the convolution, but that's really it. In fact, I think we might even know exactly what this is. I think we can just substitute 2 for 4, and what do we get? T sine of 4t over 2. So I think we'll get T sine of 2t over 2. Yeah, because just the 2 gets switched with 4. And now we were able to avoid all of that partial fraction manipulation. All right, let's see if I had anything else. That might be it. Yep, that is it. So you're welcome to stick around and ask questions. Otherwise, I will see you guys on Friday.
To view the next video in this series, click the link on the right. To view the last video in this series, click the link on the left. If you want to learn more about me, the nerd who's making these videos, visit the website below. And as always, have a good day.